time for us to do some practice problems involving numerical integration. Our goal being, let's break things into small parts, add the parts up together, and get a good approximation to an integral that for whatever reason we're having a hard time finding the integral for, by either we don't know the antiderivative or we just don't have the function, so we can't take an antiderivative to begin with. I will say, before we begin, that numerical integration is something beloved by computers. They love taking things and breaking things into lots of little teeny tiny pieces and adding them up. Computers love adding things together. It's one of the best things that they can do. But for us, we can find it a little bit tedious. So in our examples, we're just doing some very small basic examples, ones that we can have relatively small numbers where we can add things together. Keep in mind that in the real world, you'd let a computer do this because, again, if you ask it to add 1,000,000 numbers, the computer's like, woohoo, I get to add 1,000,000 numbers! Whereas if you ask a person to do it, they're like, so anyways. How do you get good at doing numerical integration? Well, the key is know your formulas and do practice. If you're following along with the video, make use of the pause button. See a problem that you like? Go ahead and pause it. Try it out yourself first, and then see how your answers compare. Well, let's begin. Our first problem. Use the 3 different type of Riemann sums, left, right, and center. Ooh, it sounds like a political show, right? Left, right, and center. Well, anyways, with 4 strips of equal width to approximate the integral from 0 to 2 of 34 over 1 plus x to the 4th dx. So this is the graph of 34 over 1 plus x to the 4th. It's, well, you can see it has a dramatic change as we go from 0 to 2. So, how do we go about this? Well, we're told 4 strips of equal width. So what we have to do is we say, all right, we're going to break up our input into 4 parts. Okay, well that's not so hard to do because we say, look, we're going between 0 and 2. So if we want to go from 0 and end at 2, that's a distance of 2. And if we want to break into 4 parts, well, the widths are 2 over 4. So we can talk about our widths, if you like, our change in x. It's 2 over 4, which really, you should think of that as b minus a over n, where we're going between a to b, and n is the number of pieces. So for us, all right, that's not so bad. You have a 1, and then you have a half, and then you have 3 halves. All right. Now, remember, we're going to do it 3 different ways. These are the 3 different Riemann sums. So we have to think about what's happening for each interval. So for convenience, let's call this our f of x. And let's go through it one at a time. So let's start with the left hand. What does that mean? Well, it means for each interval, so if I have an interval here, I'm going to go with the left endpoint. The left endpoint, all right? Good. So we're going to say, look, we're going to take our width, our b minus a over n. So that's a half. Okay, so this is our left. And then we're going to say, for each interval, we take the left ends. So the left end of 0 to a half would be 0. A half to 1 would be 1. 1 to 3 halves would be 1. 3 halves to 2 would be 3 halves. So you see we're always picking the left. So that would be what? Well, it would be our function at 0 plus our function at a half plus our function at 1 plus our function at 3 halves. And that's actually what we have to do. Now, what does that become? Well, plug things in. You get a half. Function at 0, 34 over 1 plus 0. That's not so bad. 34 plus our function at a half. Well, that's 34 over 1 plus 1/16, whatever that turns out to be, plus our function at 1, well, 34 over 1 plus 1, and 34 over 1 plus, well, okay, that's a little bit bigger. 3 halves to the fourth. Well, 3 to the fourth is 81, so you get 81 fourths. Now, if you like, you can do a little bit of cleaning up. That's not so bad. So, for instance, if you multiply top and bottom by 16 here, notice on the denominator you'll get 16 plus 1, which is 17, which goes into 34, and leaves you with the 2. So what ends up happening is you'll get a 34 from the first term. This simplifies to 32. This one simplifies to 17. And then this one, well, whoops, 81, not 81 over 4, 81 over 16, because it's 2 to the fourth, which is 16. Again, you can multiply top and bottom by 16, but now what are you going to end up with? It may not simplify nicely. Well, okay, so we have 34 times 16, because I'm multiplying by 16, and 16 plus 81. Well, 16 plus 81 gives us 97. And 97, well, that number really doesn't simplify. So, at least not in any way that would help when we're looking at 34 times 16. So, we say, great, well, we'll just leave it like that. That's okay. Not everything has to simplify. Some things, they won't. And that's just the way it is. Okay, so that's our left endpoint. All right, what about the right endpoint? So where does the right endpoint go? Well, for the right, it's still the 1/2, because that's the width of each piece. And then what you do is for every interval, you pick the right end. So for 0 to 1/2, you'd pick a half. A half to 1, you'd pick 1. 1 to 3 halves, you'd pick 3 halves, and 3 halves to 2, you'd pick 2. So you're like, great. Perfect. There you go. So it'd be 1/2, and the function at a half, plus the function at 1, plus the function at 3 halves, plus the function at 2. In other words, because we're splitting it up into 4 parts, we'll have 4 terms. All right, well, what does this become? Well, we can actually do this because we can actually say, look, it's almost the same as the left. The only difference is the sort of extreme terms. So we don't have the F0, but we do have an F2. But the other pieces are going to match. In other words, this F of a half plus F of 1, see, that's the same. Good. Actually, it goes even further. See, look, 3 out of the 4 terms match. The only thing that doesn't is the ends. So we can say, look, I can just copy. So a half, 32, and 17, and whatever this number is, well, use a calculator, that'll tell you, plus the function at 2. Well, we can do that. Look, 2 to the fourth is 16, plus 1 is 17, and 34 over 17 is 2. And there we go. That's what it would be. And if we wanted it a little bit nicer, okay, use a calculator. No worries. Now we have one more to do, which is the center, also known as the midpoint. So we'll use M for midpoint, but this is our center. And what does that mean? Well, it means for every interval, we're going to be looking at the center of that point, that interval. That's where we're going to plug in. So we're going to go halfway in between. So it's completely different from the left and the right. Because what do we have? Well, it's still a half. That's our width. But between 0 and a half, the halfway is a fourth. Between a half and 1, halfway in between is 3/4. Between 1 and 3 halves, halfway between there, well, that's 1 1/4. But we can do slightly better. That's 5/4. So function at 5/4. And then between 3 halves and 2, well, that'll be the function at 7/4. And there you go. So that's a half, and, well, 34 over 1 plus 1/4 to the fourth, plus 34 over 1 plus 3/4 to the fourth, plus 34 over 1 plus 5/4 to the fourth, and 34 over 1 plus 7/4 to the fourth. I should be careful there with my parentheses, and we'll just leave it at that. If we wanted something more precise, pull out a calculator, no problem, and there you go. All right, so this should feel familiar, almost like we've done it before, because we've done this kind of thing before. These are Riemann sums. These are the things we talked about when we first started dipping our toes into integration. All right, well, let's do something a little bit more fresh, something more new. What's that? Well, let's look at the next problem. Use the trapezoid rule with 4 strips of equal width to approximate our integral from 0 to 2 of 34 over 1 plus x to the fourth dx. All right, so we have to think about, okay, what are our widths? And, well, okay, so our widths, b minus a over n. In our case, 2 minus 0 over 4, which is a half. And we can see how to split it up. We just split it in half and split it in half again. All right, so there we have our points. So the trapezoid rule says, look, we're going to use all 5 of these pieces of information. 5 pieces of information. You might think, wait, but there's 4 strips, right? We're going to use both the endpoints in a sense. So what's the key to doing the trapezoid rule? Well, the way I like to remember it is to say, hey, there's this pattern, 1, 2, 2, 2, and 2, 1. So that's how much I want to weight each data point by. So in particular, I'll weight the data points at the end, weight 1, and the data points in the middle, weight 2. So that somehow like the ends are only worth half as much. But we have 2 ends, so it's like, oh, okay, so that means everything is about roughly equal if we just sort of think about averaging the ends. Okay, so where do we go? Well, what do we need? The formula says you're going to have a 1/2 delta x times our function at the left end, 0. Okay, so that's our 1. Now we're going to double the things in the middle. 2f of a half, 2f of 1, 2f of 3 halves. And now that we're at the other end, we're just going to have one of those, so f of 2. Now, where does the half come from? Well, we could say it's the formula, but another way to think about it is that the way that the trapezoid works is says for every strip, we're really using both endpoints for information. So I have a 1 to 2. So one strip, I use 2 pieces of information. So that's why I need to have this extra factor of a half. So for us, well, we have a half times delta x, which is a half. So 1/4. F of 0. Well, that's 34 over 1 plus 0. 34. Plus 2 times f of a half. Well, okay, if you work it out, that's 34 over 1 plus 1/16. Well, that's 34 times 16, or 16 plus 1. In other words, if you multiply top and bottom by 16, you say, well, great, look, 16 plus 1 is 17, and then that goes into 34, and that leaves us with 32. So it's 2 times 32. F of 1, well, that would be 1 plus 1, which is 2. Divide that by 34, that would be 17. So it's 2, don't forget the 2, times 17. Plus 2, f of 3 halves, well, that'd be 34, or 1 plus 3 halves to the fourth, which, okay, if you multiply top and bottom by 16, that's 34 times 16 over 16 plus 81. All right, well, which is 34 times 16 over 97, whatever that turns out to be. So 34 times 16 over 97. And when we plug in 2, 2 to the 4th is 16 plus 1 is 17. That does divide into 34 nicely, and that's just a 2. And really it's a 1 times that. And there we go. That's the estimate. Now, of course, if we had a calculator, we could go work things out. Well, that's not a nice number. But oftentimes in numerical integration, you're adding up lots of little tiny pieces, and it's not unusual for the little tiny pieces to not be nice. So because we're not asked to simplify, we won't simplify. And there we go. Okay, well, this doesn't seem so bad. And really, it's not. The hard part about numerical integration is you have to know the formula, and you have to be patient, because there's lots of little parts that you have to make sure you combine together. So as long as you can do those two things, know the formula and be patient, numerical integration, good stuff. Well, let's keep going. On to our next problem. It's going to feel familiar. Use Simpson's rule with 4 strips of equal width to approximate the integral from 0 to 2 of 34 over 1 plus x to the 4th dx. Okay, so what do we need to do? We have 4 strips of equal width. All right, so that says, hey, we need to break things up into 4 equally sized pieces. So our widths, that's the difference from start to finish over how many parts. So in our case, b minus a is 2, number of parts is 4. So that says we're going to have our intervals from our things are going to have width a half. And that can help us figure out our points, right? Because if we know we start at 0, then we can just say, look, go over by a half, and then go over by a half again, then go over by a half again. So if you're never sure where your end points are, or where the cut at, just start at one point and just keep adding the widths. 0 plus a half, plus a half, plus a half, plus a half. And you'll end up at the other end point. And if you don't, whoop, somewhere in the middle you made a small mistake. So what do we do now? Well, we have to think about, what does Simpson's rule say? Now, the way I like to remember Simpson's rule is there's a pattern. 1, 4, 2, 4, 2, 4, so forth and so on, out to 1. And what it says is that you take your data points and you weigh them in sort of, it feels like an unusual way. So we're not going to look at every data point and saying, oh, this has equal weight. Some data points are going to be thought of as being better capturing the behavior. And so we got to think about that. And what's really happening is, if we remember the philosophy of Simpson's rule, it says over 2 intervals, I'm going to think about the top as being almost like a parabola of some sort. So it's like we're sticking parabolas over 2 consecutive intervals. And that's where these strange things come up. So, okay, so now what do we have? Well, Simpson's rule says the following. It says our approximation, well, it's going to be 1/3 delta x, and then we're going to have to follow the pattern. So you start here at 1 and just go 1, 4, 2, 4, then end at 1. And it's important that when you're doing Simpson's rule, you have to have an even number. Well, in this case, we did. If we didn't have an even number, okay, go back and change the problem. So in our case, it would be, I'll emphasize it, 1 times f of 0 plus 4 times f of a half plus 2 times f of 1 plus 4 times f of 3 halves plus 1 times f of 2. So it's that pattern, 1, 4, 2, 4, 1. That's the important pattern. Now, the other thing you might say is, where's that third coming from? So here's where the third comes from. What happens is, when we think about 2 consecutive intervals, so these 2 consecutive intervals, what we're going to use are 6 points of data. And the way it works is we're going to use 1 point for sort of the left-hand side, 4 points for the middle and 1 point for the right-hand side. So it's 1, 4, 1. 1, 4, 1. And the reason you get that too is the 1 that's on the right matches up with a 1 that's on the left. Okay, so 6 points of data for 2 intervals. So that's where that 2 over 6, 1/3. Well, great. Now, the only thing left to do is plug in what we know. Delta x is a half. So we get 1/3 times a half, 1/6. F of 0, all right, that's easy. That's 34. Plus 4 times, plug in f of a half. Well, okay, that's 34 over 1 plus 1/2 to the 4th. If you multiply top and bottom by 16, you'll get 34 times 16 over 16 plus 1. Well, that's 17. 17 goes into 34, so you end up with 32. So 4 times 32. Plus 2 times, plug in 1. All right, 1 plus 1, 2. So we get 17. Plus 4 times, well, plug in 3 halves. Okay, so that's 34 over 1 plus 3 halves to the 4th. And if you multiply top and bottom by 16, you'll get 34 times 16 upstairs, downstairs 16 plus 81, which is 34 times 16 over 97. Well, sometimes that's just the way it is. So 34, that's a 16 there, not 19. So 34 times 16 over 97. All right, and then finally, 1 times f of 2. Well, that one we can do. 2 to the 4th is 16, add 1 is 17, and dividing the 34 gives us 2. And there we go. Now, on a side note, we've done this problem multiple times, but where we've changed. Sometimes we did this problem with a Riemann sum, we did it with a trapezoid, we did it with a Simpsons. And if you look at the answers, we didn't actually compute it all the way out, but if you were very patient and you did compute it all the way out, you would see that they're all different. They're all different answers. That's okay, because they're all estimates. And it's not unusual to say, oh, one estimate is here and a different estimate is there. And they can actually vary pretty significantly, especially if you compare things like the left hand versus the right hand. That's not to say that any of them are bad, but it is to say some of them can be better. And as a general rule of thumb, so here's our thumb. Our general rule of thumb says trapezoid generally does better than a Riemann sum, and Simpsons generally does better than trapezoid. So if you had to, in a pinch, Simpsons would be the best choice. All right, good. Remember, we're stuck on that desert island, right? We only have our coconuts to get us by. Well, someday it's going to happen. And then we'll be like, wow, I knew it. I prepared. Thank goodness I paid attention in calculus. All right, well, let's go on to our next problem. Use trapezoid and Simpson's rules with 4 intervals of equal width to approximate the integral from 0 to 4 of x to the 4th dx. Okay, great. So we're going to try to figure out what's this integral from 0 to 4 of x to the 4th dx. One of the things is we could actually do this integral, so maybe we can compare, right? We can say, well, let's see how they stack up. But first off, let's do the rules. Okay, so the nice thing is they kind of gave us some clues here, right? 4 intervals of equal width. We're going from 0 to 4, so 4 equal widths would make it length 1, because we have b minus a. Okay, so b minus a, 4 minus 0 over 4. So that's good. So delta x is 1, and that's the same for both of these, because each one of them involves 4 intervals. Great, perfect. So trapezoid, okay, what's the pattern? 1, 2, 2, 2, 1. That's our trapezoid. And so we have our 1/2 delta x, And remember the trapezoid, that has that factor of a half, because for every interval, we're using 2 pieces of data. Okay, so that would be what? Well, we're going to use our, starting here, 1 times f of 0 plus 2 times f of 1 plus 2f of 2 plus 2f of 3 plus 1 times f of 4. Okay, so that's going to be a 1/2 times 1. And now we say, look, our function is x to the 4th. So we can compute these. 0 to the 4th is 0. Then we have 2 times 1 to the 4th, which is 1. 2 times 2 to the 4th, well, that's 2 times 16. 2 times 3 to the 4th, that's 2 times 81. And then we have 4 to the 4th, which is 256. All right, great. So there we go. Let's actually, I do want to push a little bit and see how we do. And let's see, what can we do? Well, if we divide, look, there's a factor of half. You multiply it through. This is really the same as 1 plus 16 plus 81 plus 128. Okay, well, if we add 81 plus 128, that would be 209. Add 1 more, it gets you to 210. Add 16 more, it gives you 226. All right, so there's our estimate from the trapezoid rule. Okay, now, Simpson's rule. Okay, so what's going to happen here? Well, the right pattern is 1, 4, 2, 4, 1. Okay, this is our Simpson's rule, and it's 1/3, and that 1/3, the way you can think of it is that we're weighing things, right? And so not everything gets the same weight, so we have to make sure that we scale so at the end, every interval essentially gets 1 measurement, or the equivalent of 1 measurement. And if you look at it, look, add these numbers up. 1 plus 4 plus 2 plus 4 plus 1, that's 12. So it's like we're taking 12 measurements, but we only have 4 intervals. So I have to divide by that factor of 3. So it says, okay, so on average, we're like 1 measurement per interval. So that's another way to see it. So 1/3 delta x, and it's follow the pattern. 1 times f of 0 plus 4 times f of 1 plus 2 times f of 2 plus 4 times f of 3 plus 1 times f of 4. Great. Well, okay, we can work with that. So that's 1/3, the delta x being 1. And we actually computed these numbers, right? So it's 0 plus 4 times 1 plus 2 times 16 plus 4 times 81 plus 256. Well, this one might be a little bit more work for us to do, but that's okay. We don't mind work. I mean, we're mathematicians. We're all friends here. So let's see, we got 4. Then here would be 32. And this number, whoa, 4 times 81, 324. Wow, what a number. What a glorious number. Okay, 324 plus 256. Well, that's not too bad. What would that be? Well, it'd be 580 if we added those two together. Well, plus 32 more, 612, plus 4 more, 616. So that's 1/3 times 616, or really 616 over 3. Now, there should be a rough check. What's the rough check? The rough check should say, hey, we actually have done 2 estimates now. And what should be true is that we're both estimating the same thing, so our estimates should be reasonable when we compare them to each other. They shouldn't be the same. That would be a really weird thing. It could happen, but generally speaking, the estimates won't be the same, but they'll be close. Is 616 divided by 3 close to 226? Well, 600 divided by 3 would be like 200. And if you look, to do a little bit more, this is 205.33333. That's not so far off from 226. You know, they're within less than 10%. And we would expect there to be error. So we're not surprised that, they're not super close because we didn't take very many subdivisions. See, that's a pretty big chunk when we think about integration. The integration says, look, make things very, very small. So this is not unreasonable. If it had been the case that this was 200 and this had been like 700, we'd be like, whoa, hold on, something's wrong. We would have to back up and say, wait, our estimates are way too far off from each other. That means a mistake has happened. All right, so before we leave this problem, let's actually take some time and ask ourselves the question, what is the answer? See, we've said, well, we expect our two rules, right? There's trapezoid and Simpson's. We should think that between them, Simpson's should be better. Let's find out. So, for reference, if you work this out, this is 205.333. And just in case we need to compare, because we'll need to compare. So, here we go. The actual. What really is happening here? All right. Well, the thing is, we can do it. Not all the integrals we can, but this one we can. So this is 0 to the fourth, 0 integral 0 to 4 x to the fourth dx. Well, that's 1/5 x to the fifth from 0 to 4. Okay, well, that's 1/5 4 to the fifth. Now, what is 4 to the fifth? Well, it is, of course, well, maybe that's not so obvious, but it's not so bad. 4 is 2 squared, so it's really like 2 to the 10th, and then you get your powers of 2, right? So you get your 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. That's what it is. So this is 1/5 of 1024, which is what? Well, that's 204. If you take 1020 divided by 5, you get 204. And then you have 4 over 5, which is 0.8. Now look, the Simpsons was really close. We were within 0.533, almost only a half off. And trapezoid, well, we were off 10%, but that's the thing. Trapezoid, you kind of anticipate that you're going to be off. So you got to be careful there. All right, great. Well, cool, good stuff. Let's keep going. More problems to do, right? Always more problems to do. So, our next problem. You are in charge of a plant which is processing ore. During a 6-hour shift, you have the following data. So we have this time, t, where t is the number of hours since the shift started, and some data f of t is the number of tons per hour being processed at time t. And it says, using all the above data and the trapezoid rule, estimate the total amount of ore processed in the shift. So what happens? Well, we have a rate. We know the rate at which ore is being processed, and the question is, what's the total amount that was processed? Now, the thing is, you'll notice our rate is varying. And what we really have is we have sort of captured some data. So that in essence, we say, look, at time 0, well, we were at 5. At time 1, we were at 3. And then we got really down low, 1, then 4, then 4, then 5, then 3. So the rate at which we process ore varies over time. So we've been given little sample data, little tiny snapshots. Now, what's going to happen is it's going to vary. Now, we don't know exactly what's happening in between. We can kind of imagine, who knows? Maybe it's something, I don't know. It's something. We don't know. We don't know what's happening in between, times 0 and 1, or between times 1 and 2. We only know what's happening at our snapshot points. So we want to say, okay, great. Well, what's happening? Well, in this case, we can say, look, if this is our rate of change, then the total amount that was processed is equal to the area. So we can think of as saying, I'm really after looking for this. What am I looking for? Well, the area here. Yeah, there you go. Great. Good. So we can say, aha, we're looking for the area. But really, when we talk about the area, we're really meaning the total. Not every integral problem is an area problem. You can use integration for all sorts of wonderful things. All right, well, what do we have? Part A says the trapezoid rule, right? So what do we know? Well, we know our delta x is 1, because we're going to use all the data, and so our time steps are 1. So that's our delta x. So our formula would be 1/3 delta x times, and remember the pattern for the trapezoid rule, it's going to be a 1, 2, 2, and so forth and so on to the end. So in our case, we're going to have 1 times 5, 2 times 3, 2 times 1, 2 times 4, 2 times 4, 2 times 5, and 1 times 3. So that pattern, right? 1, 2, 2, 2, 2, 2, 1. Okay, and the delta x is 1. Okay, so that's 1/3. And here we have 5 plus 6 plus 2 plus 8 plus 8 plus 10 plus 3. Well, okay, let's see. Let's try to add these up. Well, okay, 5 and 6 makes 11. 2 and 8 makes 10. 10 makes 10, and then if you add the 8 and the 3 together, that makes another 11. So you really have what? We have a 21 and another 21. That makes 42. And so we say, okay, 1/3 of 42 would give us 14. All right. So what does that mean? That means we've done 14 tons. What do you get? Another problem done. Yeah, wait, no, that's not the song. Okay. All right, good. Now, let's go to Simpson's rule. Okay, so what is Simpson's rule? That's part B. It says use all the data and Simpson's rule to estimate the amount of ore processed. Well, all right. So we have delta x is 1. And now what's the pattern for Simpson's rule? It's 1, 4, 2, 4, 2, so forth and so on, ending with a 4, 1. And, whoops. I made a mistake here. Let's go back and fix it. 1/3 is not what you need for the trapezoid rule. It should be a half. So this should have been a half. So this should have been a half, which means, whoops, well, good to catch them early, 21. Sorry about that. Okay, you gotta keep track. This is one of those things that it's a dangerous thing when you have so many rules. They start to blur together. So it's good to go back and say, okay, wait, why do we have that factor? Where is that 1/3 coming from? Because they're not like magical numbers that are just there because, well, they have to be there. They represent things. Okay, so here we go. Simpson's rule. So why does Simpsons have the 1/3? Well, it's because for every 2 consecutive intervals, we're using 6 points of data. 2 over 6 is 1/3. So we have 1/3, and now we're just going to follow along. So 1/3 times delta x, which is 1, and here we go. 1 times 5, which is 5. 3 times 4, 12. 2 times 1, 2. 4 times 4, 16. Ooh, that's a big number. 2 times 4, 8. 5 times 4, 20. And 1 times 3, 3. All right, so, well, what does that give us? Okay, so do some more combining here. Let's see, 5 and 12 and 2. Well, if we combine those together, that's 19. And if we combine the 8 and the 3, that would be 11 which is convenient, right? Because 19 plus 11 makes 30, plus 20 makes 50, plus 16 makes 66. So 1/3 times 66, which is 22. 22 tons. All right, good. Now, you might say, cool, what's the correct answer? How much ore did we actually process? And the answer is, we don't know. It's hard to say. So you might say, well, okay, so what number do you report? Well, it depends. If you want to say, on average, we believe the Simpsons is more accurate, then you would say, let's use Simpson's rule, and we'll report that because that's a better method in general. But of course, you might say, well, for various regulatory purposes, we will report the smaller number. That sounds like you're starting to think of calculus as a tool to be used for evil. No, calculus is a tool for good. All right, so be good. Okay, all right, well, let's try another problem. So we can get good, right? That's what we want. So, our next problem. Use the picture of the curve y equals f of x below to do the following. And part A, estimate the area under f of x, where x goes from 1 to 9, using the trapezoid rule with 4 equal intervals. And B, estimate the area, same thing, but with Simpson's rule. Now, if you think about the previous problem said, I'm going to give you data as a table. So in other words, I'm going to give you a function as sort of like some sampled points. Here, we're going to have a slightly different situation, which says, I'm going to give you a function as a picture. And it's like, ooh, do we know what the function is? And the answer is no, we don't know what the function is, but we know the visual representation of the function, and we can use that to gather data. Now, in particular, if I'm going from 1 to 9, and I have 4 equal intervals, well, what's our delta x? So in both cases, same thing, right? 9 minus 1 over 4. 9 minus 1 is 8. 8 over 4 is 2. Which means we're going to sample at the key points. So what we really want is to focus on what's happening to our function at 1, 3, 5, 7, 9. So we say, okay, there's 1, 3, 5, 7, and 9. Because when we talk about using something like Simpson's rule or trapezoid rule, it's really saying we're going to look at some key points and use the information there. So it's like we're not even going to pay attention to exactly what the curve looks like in between. In fact, for our purposes, we don't know. We could, as far as the computation, it takes no consideration into how the curve in between looks. It just says it's going to do something. All right, well, so we're almost done. In some sense, we just have to write the stuff down. So let's do part A. Now, trapezoid rule, remember that's the pattern where it's 1, 2, 2, 2, 2, 2, until the very end as a 1 again. And so we're going to have what? Well, we're going to have 1/2, because trapezoid rule, for every one interval, we use 2 pieces of data. So we need to have a 1 over 2. Then our delta x is 2. So 1/2 times delta x, b minus a over n, times, and now we do our sample data. It's going to be 1 times what happens at 1. Okay, so if we want, we'll write it as this way. 1 times f of 1 plus 2 times f of 3 plus 2 times f of 5 plus 2 times f of 7 plus f of 9. And there's a 1 times there. Now, for us, the half times the 2, well, that's nice. Okay, so what do we end up with? Well, start reading it off. F of 1 is 1. So we get 1. And then we have 2 times f of 3. So that's 4. Plus 2 times f of 5 is 3. plus 2 times f of 7 is 4 again, plus 1 times f of 9, which is 6. Okay, so, well, other than my hand going up a hill for some reason, we have 1 plus 8 plus 12 plus 8 plus 16. Sorry, not 16, 6. There's a times in there. It's nice to be able to read your own handwriting, right? 1 times 6. Okay, so let's see, there's a 28 there, plus 7, and the end makes it 35. All right, there we go, 35. All right, good. Well, now let's do B, Simpsons. Well, what's that pattern? Well, that's our 1, 4, 2, 4, so forth and so on, ending with 4, 1. Okay, so what do we have? Well, 1/3, and remember, for every 2 intervals, we're grabbing 6 pieces of data. And so that's why 2 to 6, 1/3. And then the delta x is 2. And then it's the pattern. 1 times f of 1, 4 times f of 3, 2 times f of 5, f of 5, 4 times f of 7, and back to 1 at the end, f of 9. And we actually know these numbers, f of 1, f of 3, f of 5, f of 7, f of 9. It's the same numbers that we saw there. So what do we have? That's 2/3. So 1 times f of 1 is 1. 4 times f of 3, well, that's 4 times 4, 16. 2 times f of 5 is 2 times 3, which is 6. 4 times f of 7, that's 4 times 4, which is 16. And then f of 9, well, that'd be 6 again. All right, great. Well, so now we add. Okay, good. Something seems suspicious to me. I'm going to come back to that. I think I made an error up there. Let me finish this one here. 16 plus 6 is 32, plus 32 makes 64, plus 1 more makes 65. Okay, so this looks like 2/3 times 65. Or if you like, that'd be 130 over 3. Well, 130 over 3, that's about 43.33. It's a little bit big when we think about that. Let's double check our work, right? It's always good to double check because, you don't want to make mistakes. Or if you do, you want them to be small mistakes. Okay, so the pattern is fine. That's 1, 2, 2, 2, 1. So we still have the 1, 4, 3, 4, 6. And now 2 times 4 is 8. 2 times 3, that's not 12. 2 times 3, that's 6. And 2 times 4 is 8 plus 6. So look, this 35, that's off. What should it have been? Okay, well, it should have been 6 plus 6 is 12, plus 8 makes 20, plus 9 more, 29. All right, now let's check this data. Okay, 1 times 1, 4 times 4, 2 times 3, 4 times 4, and 1 times 6. Okay, that's fine. And now, what do we get? Well, okay, 32 plus 30. Oh, wait a second, hold on. 16 plus 6 is 22. It's 22 plus 22 makes 44 plus 1 more. That makes 45. Wow, lots of errors. Good thing we went back and checked our work. 45 divided by 3 is 15 times 2 makes 30. Okay, and now that feels better because the estimates we got should be close to each other. And initially, when we did the work, or rather, I did the mistakes. These are all my mistakes. the numbers weren't kind of close. They were kind of far off for what I would expect, because this is not really an unreasonable function. They should both be relatively close to each other. That are two approximations if our function isn't behaving too erratically. As a general rule, the more sort of tame our function is, in other words, there's not massive swings, then we would expect our estimates should be both relatively reasonable, and therefore they should have been both close to each other. And when they weren't, okay, mistakes were made. But that's all right. We said, okay, since we know mistakes were made, let's go back, let's fix our mistakes. It's nice to be able to go back and fix mistakes, right? If only all of life were that way, where we could go back and fix our mistakes. It would be better. It would make the world a nicer place. All right, well, let's keep going. All right, on to our next problem. So, during a heavy snowstorm early in the season, you were measuring the rate of snowfall at regular 1-hour intervals from the start of the storm. While preparing a summary of all snowfall over the entire season, you find that you have lost the data for this particular storm at the 2 and 5 hour marks. You do, however, still have the following data. Okay, so we have some data, but not all the data. We're missing 2 pieces of information. Searching through your notes, you see that before you lost the data, you had estimated the total number of inches which fell during the storm. Now, using all the data, including the missing data, the estimate, if you used the trapezoid rule, was 20. And the estimate, if you used Simpson's rule, was 22. Now, use the information to fill in the missing entries. All right. So it's like, okay, what do we have? There's 2 things we don't know, but we also have 2 pieces of information. In other words, what we have is what our estimates are based off of Simpson's rule and trapezoid rule. All right, so let's just mark the 2 things we don't know. We'll give them names temporarily. Let's call them A and B. So those are what we're trying to solve for. Solve for A, solve for B. And we take a look and we say, all right, well, we can find the total, by the way. We should point out, since we have a rate of snowfall, if you integrate the rate of snowfall, you find the snowfall. So it really is, this is an integration problem, and we're using some numerical integration to find the total snowfall. Now, let's look at a few pieces. Well, one thing is, what can we say about our delta x? Well, we look at our spacing, and we see, delta x is 1. Okay, great. So let's go and talk about our 2 rules, the trapezoid rule and the Simpson's rule. So if we use the trapezoid rule, what do we have? Well, according to this, the trapezoid rule gave 20 inches. So 20 is the result of applying the trapezoid rule. Okay, so how does that work? The trapezoid rule has that factor 1/2, right? Because for every interval, we look at both the left and the right endpoint. So there's 2 pieces of information for every one interval. That's where the 1/2 comes from. Delta x, 1. And now we have to think of the pattern. Well, what's the pattern? Well, for the trapezoid rule, it goes 1, then 2, 2, 2, 2, 2, 1. That's the pattern. So in essence, all the middle points are equally weighted, and the endpoints are half as much, right? So what do we have? Well, we're going to have 1 times 2, 2, 2 times 1, 2, 2 times A, 2A, 2 times 5, 10, 2 times 3, 6, 2 times B, 2B, or is it not 2B? Oh, it is 2B. All right, and 1 times 4, 4. All right, well, let's see. What can that become? Well, 2 and 2 is 4, plus 10, that's 16, plus 6 is 22. Plus 4 makes 26. Wait, did we do that right? Let's think about it a different way. 6 and 4 make 10, right? Plus 10 more makes 20. Yeah, 24. There we go. That's what it should be, 24. Okay, so we have 24 times the half. So that would be 12. And a half times 2a plus a. And then a half times 2b plus b. Or if we put it another way, a plus b should equal 8. All right, so that says that we don't know what a and b are individually, but based off of the trapezoid rule, we know if you add them together, you should get 8 out. Well, that's good, but we need more. Well, we have more. Simpson's rule, right? Okay, so let's think about Simpson's rule. Well, we know Simpson's rule, 22 inches. They might say, well, wait a second. Was there 20 inches or was there 22? And the answer is, we don't know. Because these are both estimates. That's all right. Okay, so Simpson's rule says what? Well, it has 1/3. Because for every 2 intervals, you're really reading off 6 pieces of information. So that's the 2 over 6. Okay, times the delta x, which is 1, times, okay, now we need to know the pattern. So for Simpson's rule, it would be 1, 4, 2, 4, 2, 4, 1. So in other words, it sort of oscillates. You know, these get a little bit more, and then the next one, as you go across. So what do we have? 1 times 2, 2. Oh, same as before. 4 times 1, 4. Then we have 2 times a, 2a. 4 times 5, 20. 2 times 3, 6. 4 times b, 4b. And 1 times 4, plus 4. All right, Well, 1/3 I don't think is going to divide nicely, so let's move it across. So we could say 66 is equal to, well, what? 2 plus 4 is 6, plus 20, 26, and plus 10 more, 36. And then we have 2a and 4b. Well, okay, that says 2a plus 4b, 66 subtract 36 would be 30. Okay, now divide by 2. A plus 2b had better equal 15. All right, good. So now we know a plus 2b equals 15, and a plus 1b has to equal 8. All right, well, 2 equations, 2 unknowns. Our favorite situation. Well, so what can we do? Well, we look for ways to combine. So if a plus 2b is 15 and a plus b equals 8, well, if we subtract, the a's cancel. 2b minus b is b. 15 minus 8 is 7. Okay, so b is 7. Well, what about a? Well, a plus 7 has to be 8. So that says what? A has to be 1. And so we can now fill in the missing entries, right? So A is 1 and B is 7. Good. Well, is it reasonable? Well, probably. The good news is we didn't get a negative rate of snowfall, right? That would be highly suspicious because it doesn't make sense for snow to have a negative rate of snowfall. That would be what? There was a rapid heat wave and it was melting? I don't think that's how it works. All right. And another thing that you can kind of see is you can look. See how Simpson's rule got a higher answer? Well, that's sort of indicating what? Well, it's indicating that when we look, we should expect B to sort of be a larger value, right? Because if you look at where that slot is, it's in a slot where Simpson's rule highly values it, at least comparatively to the trapezoid rule. Whereas over in A, it's sort of a lesser valued one. And so it makes sense that B should be larger. So that's good. Those are good signs that we're actually doing things correctly. And so there we go. Great. And we filled it in. So that's the problem. Aha! Wonderful. Well, good. I think we have time for one more. One more problem to finish it up. So here we go. For a less than or equal to x less than or equal to b, let's assume that our derivative is negative and our second derivative is positive. And we're going to look at the L of n, R of n, M of n, T of n. That's the left-hand rule, right-hand rule, midpoint rule, trapezoid rule. In other words, all some various ways we can do integration numerically, right? We have these different techniques. And so we're going to approximate this integral by these different rules by going from a to b, and we're splitting to n equal pieces. And the thing is, arrange these orders L of n, R of n, M of n, and T of n from smallest to largest. So our goal is, how do these things relate to one another? Okay, well, good questions here. So let's think about what's happening. So the nice thing is, look, we only really need to understand for n equals 1. If we can understand what's happening on just one slice, then we say, look, on one slice we know the inequalities, and it's going to carry through to the others. And also, this will sound strange, but try to sort of be more extreme. So don't be like, oh, it's kind of a little bit bent. No, like whoa, like really get into it, like and so okay. So I'm going to write the word extreme here, but I just really want to say we really want to try to capture behavior. So let's talk about what we know. So what do we have? We have f prime is negative. Well, what does that mean? That means our function is decreasing. And that's what it means to say that our f prime is negative. We're also told f double prime is positive. Now, that means something as well. That says, hey, our function, it's going to be concave up. All right, so we have a function which is decreasing and concave up. So let's just draw ourselves such a function. So I'm going to imagine I start here and I end here. So I need to go downhill, but because I'm concave up, well, remember concave up would be, second derivative is positive, means we have that kind of a shape. So it's going to go something like that. Okay, so this is what an example would look like. Again, it's kind of somewhat extreme, but you probably wouldn't expect it to dip quite that much inside of one interval, but we just need to understand what's happening. So, how can we think of what's going on? Well, what we can think of, if I only have one interval, let's think about where we would end up in terms of the heights. Because I can think of what's happening is I have a base, and then I want to have a height. So let's talk about our left, right, and middle. So we can spot some of these right away. The left end is up here. The right end is there. Okay, great, perfect. And so, no surprise, the left hand is going to give a larger value than the right hand because we're going downhill. So because we're going downhill, we would expect that the points towards the left-hand side will be larger than the points towards the right-hand side. Now, how about the middle? Well, the middle, you go to the middle of the interval, and you go up. So the middle would be here. So, again, not surprising. If our left is largest and our right is smallest, the middle is in between. Where does trapezoid fit in? Okay, this is the fun one. All right, how can we think of the trapezoid rule? And here's a way to do it. Take your picture and imagine that you just made a trapezoid with the left and the right ends. So, in other words, you combine these two together. Now, again, from the center, same center that we used for the midpoint, if you were to go up here, you can take this triangle, turn it upside down, and would fill that space in. So the trapezoid rule, it's equivalent to taking a rectangle that is that height. In other words, it would be from the midpoint up to the straight line connecting the two endpoints. And here's where concavity comes into play. If you only cared about decreasing, you already have, okay, how do the left, middle, and the right combine together? The concavity says I'm coming down, which means that I'm going to be below this straight line. That tells me where the trapezoid fits in. And so now we can read off our answer. So we have that the right hand estimate will be below the midpoint estimate, which will be below the trapezoid estimate, and that'll be below the left hand estimate. And that's the answer. Now, you might say, well, where's the integral? And the actual integral, I don't think we have enough information to make a decision. It's somewhere in here-ish, somewhere around there. But we're not going to worry too much about that. We already have what we asked for. How do we put these in order from smallest to largest? So we're done. A great place for us to stop. Thanks for coming, and I hope you enjoyed it, and hope you come back. Bye.